One of the video notes for Objective 1E, inverse functions. In this part of the video notes, we're going to talk about inverses from graphs and tables. And then in part 2, we'll talk about inverse functions algebraically and just some properties of a function and its inverse. So the first thing in our notes are some definitions. We want to talk about one-to-one. A function is invertible or has an inverse if it's a one-to-one function. And so the first way we want to test for a function to be one-to-one is from a graph. Because in a table or in a mapping, it's really easy to tell that a function is one-to-one if it doesn't repeat y values, which is essentially what you're looking for. An equation, graph, table, mapping is a function when it doesn't repeat x values, and it's a one-to-one function when it doesn't repeat x or y values. So we have this thing called the vertical line test, and the vertical line test tells us that something is a function. For example, this quadratic passes the vertical line test because I can align a vertical line through the picture and it only ever intersects the graph once. On the flip side, if we want to tell a function is one-to-one or if a function has an inverse, we can use what's called the horizontal line test. And you can see the quadratic passes the horizontal line test at its vertex, but fails the horizontal line test everywhere else because it intersects the horizontal line twice. So as far as a horizontal line test, a quadratic function fails. Quadratic functions, or really all even functions, are not one-to-one and do not have inverses unless you restrict their domains. So what I mean by restricting the domain on this function is if we just ignored half. If that half of the function wasn't there, then it would pass the vertical line test. And this is how we achieve the results of the square root function being the inverse of the quadratic function. Speaking of the square root function, let's take a look at example 2 in the notes, which happens to be the square root function. Is this function invertible? It's a function because it passes the vertical line test, and it's an invertible function, or a one-to-one function, because it does pass the horizontal line test. Next up in our notes, we want to be able to find inverses from maps and from tables. So example 3 is an example of a mapping. And a mapping lists the domain in one side and the range in the other. And then these domain and range usually are listed in increasing order. This example happens not to be. But then it corresponds each point with an arrow. So how are the values corresponded? We have 2, 3. We have 5, 6. We have 4, 10. And we have 1, 20. Well, an inverse function is a function that takes each value of the range and maps it to each value of the domain. So the inverse is really just a switching of x and y. The inverse function here is 3, 2, 6, 5, 10, 4, and 20, 1. And if we wanted to draw this inverse as a mapping, we would just switch these circles and switch all of the arrows. So as a mapping, f inverse, this is the notation we use for an inverse function, is to the -1 power. Our domain bubble will now be 3, 6, 10, 20, and our range bubble will now be 1, 2, 4, and 5. And you can see that I did put them in increasing order, which is the way that a relation mapping should be drawn. So we have 3 to 2, 6 to 5, 20 to 1, and 10 to 4. This is the inverse mapping. Tables, very similar. You just want to swap your inputs and your outputs. So the first table we have is example 4, and that table is x, y, -2, -2, -1, 2, 0, 6, 1, 10, and 2, 14. How are the values of the domain corresponded to the values of the range? Well, the table is a direct correspondence. So what is the inverse function? And I'm going to switch to function notation for my inverse. All of these y's will become the domain, and all of these x's will become the range. And again, this function is invertible. This function is one-to-one because none of the y values have repeated. You can imagine if any of these y values repeated, when I inverted it, I wouldn't have a function and therefore couldn't have an inverse function. There are two problems for you to practice. Go ahead and try those problems now. There's a trick to one of the questions that I'm going to reveal in this video, so you'll want to pause and give both of those problems a try. The inverse function of the first practice problem is 1, 1, 4, 2, 9, 3, 16, 4, and 25, 5. But the second practice problem does not have an inverse because the second practice problem is not one-to-one. And we can tell it's not one-to-one because if you look at the arrows, both -1 and +1 point to 5. And so 5 has been repeated, which means there is no inverse function. The last portion of these video notes is finding an inverse from a graph. And there's two different ways to approach finding an inverse. You can use a reflection, or you can use the idea that you just need to swap the x and the y. Example 5 brings back our square root function, so just a typical square root, and I'm going to try to be accurate with my points here. If we need to switch x and y, we can make a table of the points on the graph, swap the table, and regraph it. And so I'm going to demonstrate that method for finding an inverse. So the points in this graph are 0, 0, 1, 1, and 4, 2. If I inverse those ordered pairs, I will be graphing 0, 0, 1, 1, and 2, 4. And so the inverse function is half of a quadratic. Now an inverse function is a reflection over the line y equals x. And this is why the x and the y coordinates swap, because y is equal to x. So we just draw this line. And if you're good with reflections or just visual mathematics at all, you can see that the purple line or purple curve has just been reflected across the green y equals x slant line. We'll try this again in example 6 with a slightly more complex graph that's going to take me a little bit more time to draw. And the process of finding those points is one way to find the inverse of this graph. So I'm going to center this. And I'm just going to identify some points from this curved figure that we can then use to make an inverse function. And so it doesn't look like any ordered pair other than -1, 1 are really equal on the intersection, except maybe -4, -3. And that's about it. So I need to point up between 2 and 3, and my arrow is at 4, and I need to curve down to this point, cross the x-axis near -3, and from this point, curve again. Well, before I take the time to invert this function, I just want to make sure that it passes the horizontal line test. And so if you draw your curves appropriately, your pen should not pass the graph more than once, which means it does pass. The shape of this graph is actually going to be difficult to draw without more ordered pairs. So if you have a difficult time reflecting visually, it might be to your benefit to estimate some of these points to the nearest tenth in order to get your inverse. I'm going to attempt to draw this inverse just based on the line of reflection. So there's my line of reflection. And to reflect over a line, you need to be equidistant on both sides. So I'm going to start with this arrow being the same distance below the line as it is across it. And then this curve goes towards the line, hits a point right there, curves out to a point right there, curves back in towards the line, and ends in an arrow, like that. And so an inverse graph will be equidistant on either side of the line y equals x. This concludes the part 1 of the video notes, where we just focused on functions represented as graphs, tables, and maps. In part 2, we're going to algebraically solve to find an inverse function.